In this video capsule, we shall discuss the isolated converters. Till now, we had been discussing on the non-isolated converters like the buck boost and the buck boost converters. These were called the primary converters. Using these primary converters, other converters are derived, called the derived converters. And among the derived converters, the isolated converters are also part. We shall introduce in this session, in this week's session, an important component called the transformer, a high frequency transformer that will play a very important role in the isolated converters. The transformers do two main functions. One is to provide isolation, that is physical separation, galvanic isolation between the output part of the circuit and the input part of the circuit. Another important feature is the turns ratio. You have scope to design the turns ratio appropriately so that you can have a wide operating range. We shall definitely look at the design of the transformer both electrically and magnetically and see how to choose the core and also to design the windings. And we shall look at how to solve some of the magnetic issues that will come, like core saturation and things like that. Even the inductor, we will take the design values that we learned in the last week and build the inductor, a physical inductor. We need to choose the core for the inductor and we need to determine the windings and see how to introduce the air gap. These physical issues and magnetic issues will be addressed in this course. So this week will focus more on these isolated converters with a bit more emphasis on the isolation components, magnetic components like the transformer and the inductor. So we will discuss the forward converter, which is one of the buck-derived converters. Other buck-derived converters are the push-pull, the half-bridge and the full-bridge converters. The other family of converter that we will discuss is the buck-boost family. One of the most popular buck-boost derived converter is the flyback converter, which is very, very popular and you will see it in most of the commercial power supplies. So we'll definitely have a look at it and see how we go about designing its magnetic components and isolation components. Then we will definitely have a look at simulation. We will take a few example circuits, put it through the schematic capture using GSHEM, and then use the ngSpice engine to simulate it and look at the results and see if we can get more insights into the circuits.
This is the buck converter circuit, which you are by now very familiar with. We will be starting from this non-isolated buck converter and developing the forward converter, which is an isolated converter and derived from this buck converter. All buck derived converters will have the output portion which is like this: the diode, inductor, capacitor, load combination. This portion will be the prominent feature of the output side of all buck derived converters. There will be change in the input portions. So let us start first with rearranging some of the components and see where we can put the transformer. Now this is the buck converter. We have put the switch on the positive arm of the supply. We can as well put the switch on the negative or the return path of the current without affecting the operation of this whole buck converter circuit. So let us do that. For example, let me move this down and let me move this up. Let me reverse this in such a way that it is compatible for the return path. See, the current flows in this direction and returns back in this direction. So the transistor is now compatible and made correct to the operation of the or the flow of the current. Now this is still the same old buck converter. The operation is exactly the same, and you will see that when this transistor is on, the V in potential comes across the diode, turns off the diode, and the V in potential charges the inductor, and the voltage across the inductor is V in here minus V naught here, so it is V in minus V naught during dTs period. And during the time when this is off, there is no return current here, current flow here. The inductor is freewheeling through the output capacitor and the load, and this is conducting, and this is 0. So it is 0 minus V naught. So minus V naught by L is the rate at which the current falls. So the regular operation of the buck converter remains the same. The input output relationship also remains the same. Only what we have done is we have shifted from the positive rail, we have shifted the switch from the positive rail to the negative rail. In doing this, we have made the gate drive or the base drive referred with respect to the ground point here or the negative point of the supply, which is much more easier to achieve. Next, what we will do, we will further reposition this BJT or a transistor in the following way. Let me click on this BJT switch and let me rotate it in such a way that it is facing in this fashion. Further, let me also position it such that it is in this kind of a topology. Now I will put in some labels. So let us say this is a label indicator, just like we do in SPICE, and I will say that this is V in, that is where the positive of the supply is attached, and this is the ground. Now I need not have this, I will remove these portions. So this is still the buck converter, the same old buck converter, and the operation still continues to remain same. This BJT switch, when it is on, there is a voltage V in which appears across the diode, reverse biases the diode, current flows through the inductor, charging up the inductor, and flows back in this fashion. And when this switch is off, the inductor freewheels through the output circuit. Operation remains the same, input output relationship also remains the same. Now we need to introduce a transformer. This is an appropriate place where we can introduce the transformer, and we will push the diode a bit inside and start placing the transformer there. Now what we shall do, we shall move this diode inside a bit like this. We will make some space to introduce the transformer here. So let me position it in this fashion here. So you have the transformer coming in that place there. The transformer right now is in a situation where it can operate properly when the switch is on. When the switch is on, there is a voltage appearing across the primary. That primary voltage gets transferred to the secondary, and the diode is reversed by this diode is out of the picture. The inductor gets charged, and so on. And when the switch is off, the inductor is freewheeling like this, and the secondary of the transformer is effectively short circuited, and there is no chance for the core flux to reset. And if the core flux doesn't reset in the next cycle, you will see that the moment this is on, the magnetizing current will be in such a way that it will try to saturate the core. We will more on this later, but to complete the circuit, we need to insert a diode here such that when the inductor is freewheeling, there is no short circuiting of the secondary of the transformer. This diode will prevent short circuit current in the secondary like this. This way it decouples the buck portion of the circuit. So now let me clear up the clutter and we will put the circuit neatly in the following manner. So now I have cleared up the clutter and then connected the circuit properly, and you see that this is the isolated buck converter, and this is called the forward converter. So no longer should we call this as a buck converter, it should be called the forward converter. Forward because the power is the power is sent forward into the output section during the time when the switch is on, as against the flyback converter when the power is sent into the output when the switch is off. So it's just a nomenclature and a convention. This is called the forward converter in the literature world over, so we will stick to that name. After having placed the transformer here, let us now assign the dot polarities to the primary and the secondary. So let us say that is the dot end for the primary, and likewise this is the dot end for the secondary. Assigning dot polarities is very important. You have to do that for every transformer or every coupled component that you would have. What it basically indicates is that the relative polarities of the various windings. Now in this case, when the transistor is on, this non-dot end is connected to the ground, the dot end is connected to Vin, so the dot end is positive with respect to the non-dot end. Likewise, the secondary side, the dot end would be positive with respect to the non-dot end. And when the transistor is off, there will be a reversal of the polarity where the non-dot end is positive with respect to dot end. So also on the secondary side. So it is very important that you would place the dot polarity assignments for every transformer that you would use in a circuit. Now we have to give a core reset, flux reset path for the transformer. When the BJT is off, the inductor here is freewheeling, this diode is off, the transformer secondary is open circuited, the transformer primary is also open circuited. You have to now give a path for the core flux to reset. So let us provide a resistance diode combination here such that the core flux can get reset in this path. So let me use a resistor first in this fashion, and then a diode which will get connected like this here, and then of course complete the connection by making the wire connection in this fashion. Now this circuit is a fully functional forward converter circuit. So when the transistor is on, when the switch is on here, this is at ground potential, this is at Vin potential, this diode is reverse biased and it is out of picture, this whole arm is out of the picture. So this voltage gets transferred here and charges up the inductor in the normal way. So it will be a buck converter. When the switch is off, at that point there is a reversal of polarity here. Here the inductor is freewheeling and the primary side here will freewheel in this fashion and thereby reset the core flux. So this path is very important. Without this path, this transformer isolated forward converter will not work. So this freewheeling path is a very crucial path. This is right now a lossy freewheeling path. Later on I will also touch upon lossless freewheeling paths. For now, we have to now look at the input-output relationship and then the waveforms. Before looking at the input-output relationship, let me place here the transformation ratio 1:n. Now this indicates that for every one winding there are n windings here, or just to indicate that n2 by n1 is n. If n is greater than 1, then it is step up transformer. If n is less than 1, it is a step down transformer. Now this forward converter, I have added this 1:n turns ratio. What it basically means is, for every one turn here, there are n turns in the secondary. N can be greater than 1 for stepping up, n can be less than 1 for stepping down. So now let us say that during the DTS period, this transistor is on. So what is the voltage here? The whole voltage here is Vin, and the voltage that appears across on this side is n times Vin because of the turns ratio 1:n. Now this n times Vin comes here at the pole of the buck converter, and here you are having V0. So you see that during DTS time, you have NVN minus V0 as your inductor voltage into DTS, plus during the 1 minus DTS time, this is the transistor is off. So during the 1 minus DTS time, we have the transistor going off. So let us erase these. So during the 1 minus DTS time, this is off. Now this would become plus. There will be a reversal of the polarity. There is a freewheeling through this diode. Let us say I call this diode D1, and this is at 0 volt if D1 is ideal. So you have minus V0 appearing across the inductor into 1 minus DTS. Now that should be equal to 0. This will lead you to the input-output relationship, very similar to the buck converter, except that you have a n term appearing here. So if you rewrite and solve for V0, you get V0, which is equal to n times Vn into D. So this would be the input-output relationship for the forward converter that we have shown here. And when the inductor here is freewheeling in this fashion, this diode is off, secondary is open, the primary is also freewheeling in this fashion. In the primary, this is positive with respect to the dot end, so there will be a freewheeling action happening here. Now this, the moment it is freewheeling, let us say diode is ideal, there is a L in the primary, the magnetizing inductance, and this resistance R. So in a L by R ratio, there will be a current which will be decaying. So it will be decaying with the L by R time constant exponentially. So exponentially the flux will decay. So here, if I say this is some resistance R, and if Lm is your magnetizing inductance, the current I here will have a wave shape which starts falling like that with a time constant of tau equals Lm by R. So it will have a falling time constant like this. So by the time it reaches 0 here, the core flux would have almost come to zero flux state. So this is a very important portion. The diode R combination is a very important portion of your forward converter to bring about core resetting. Of course, there is one major problem with this R. It is dissipative, so it will bring down the efficiency. Right now, we will go with this R type of core reset, lossy core reset. Later on, I will explain a method where you can have a lossless core reset too. Next, let us look at the waveforms of the forward converter, which will give us more insight and then which will lead us to the design of the various components.